Since I screwed up, so I guess I'll break them down to two parts, part one, part two, you know. So when I put this on the web, this will be work part two, the first one work part one. Forgot to record. Let's take an example now where the force, actually you're pulling a 40 kilogram, but now on an angle. Let's say the force is 100 Newton now. The angle is what? 30 degrees. And you move this box 40 kilogram. You move it how many meters? Let's say 5 meters across the whole floor, the living room. You want to put friction or no friction? None. None? Okay, no friction. So you want no friction. How much work? Find the work done by you, by us, to move the box 5 meters. How much work done by us? We move in the box. Since I'm moving the box across the room, I don't care about that force. What I care about is what portion of that force in this direction. What is that value? And that's really your f of x. And that should equal to what? 100 cosine 30 degrees. 100 cosine 30 degrees. So the work done by me or by us is equal to the force, which is what? 100 cosine 30 degrees times the distance traveled, which is 5 meters. And that's 433. 433 joules. Now notice the equation I'm using is different. I'm using this equation. I'm using F times X times cosine theta. That's the equation I'm using. When that force is not in the same direction that you're moving, you have to find the component in that direction. In the previous example, we had the force looking like this. 20, that's the force. And the box moved what? How many meters? 2 meters, I think. We said the force equals what? I mean, work equals force times distance. So work equals the force is what? 20 times the 2. I didn't use the cosine here. If I did use this equation, would that give me the same answer? Or let me rephrase the question. If I use that equation for this problem, what value should I use for theta then to give me the same answer? What is it? Not for this one. 0. Yep. If you put in 0 here, what's cosine of 0? 1. Work equals force times distance. Now let's go back to the gym, that weight, lifting weight. We talked about doing negatives. You got the weight pushing down on you. That's your force, the weight. And let's say you have, I don't know, you have 200 Newton down, and you pushing up there. Actually, the weight is down. That's you pushing up there. That's you. You got a force of up of 200 Newton. Well, it's not moving now. Once they equal, they move. What happens then? Exercise. You start basically. You're not pushing with 200. Maybe you want to push with 199, a little bit less than the 200. Once that force becomes less than this, what will happen? The weight starts to move down. So if you change that force, instead of 200 Newton, nothing's moving. Your arms are locked and you're holding the weight. And now you weaken your muscle a little bit there. You're not pushing as hard. So let's say you do 190 Newton here. Since the weight is higher than the force you're pushing, the weight starts to move down slowly. And let's say travel a distance, I don't know, what is that, half a meter? It went down this far, the length of your arms. Brought it down all the way to your chest. So what's the work done? The work done by us, not gravity. It's force times distance times cosine theta. By me, the force I'm pushing with is what? 190 Newton. The distance is how far? Half a meter. And what's the angle? Cosine, what's the angle between them? No? Remember, the weight is down. I mean, you are pushing up. That's the direction you're pushing. And which way it's moving? Down. What's that angle? What's that angle between them? 180. What's cosine of 180? Minus 1. That's where the minus came in. Because cosine of 180, remember in the first example we did the weight? Where was it? We were just talking about it somewhere. I don't know what happened to it. I lost it. Oh, right here. Friction force. We said the work done by the friction force is negative. Why? Because the angle between the friction force and which direction you're moving is what? 180 degrees. So this equation really finds the work for us for any type of a problem. So that's the equation we're going to use. We're not going to use that one anymore. Because if the angle is 0, cosine of 0 is 1. If the angle is 180, cosine 180 is negative 1. So this will take care of all of them. So that's the equation I'll be using for work. So this will be a negative what? What's 190 divided by 2? Is it 195? 95 joules. Let's try another example with work. You're an EMT. You get a call, we have a child, I don't know, was in the pool, does not swim, and he is not responding. You rush to the scene, horrible story, but you rush to the scene here, and there's start doing CPR, and thank goodness you bring the baby back to life, but now we take the baby to emergency just to make sure, check him out, or her, to make sure that baby's okay. So you get that person here, that's the patient, laying on that gurney there. So that patient has a mass of 87 kilogram.
That's a child.
What's that big child? Want a smaller one?
So big.
That's about 200 pounds, close to 200 pounds. So how about 27 kilogram? That is, I was about to use an adult, I changed the story. 27 kilogram, that's about 60 pound, 65 pound.
That's a kid.
Yep. Now you're in a rush there. You're pushing. You're actually the intern here, the nurse, whatever, the EMT. You're pushing in that direction. That's the direction you're pushing the gurney. And you're moving really fast because talking about saving somebody's life. You have an acceleration of 0.55 meters per second squared. So you start to push the baby from here to the door of the ambulance. There's the ambulance. So that distance here is 1.9 meters. You started from rest. You put the baby on the gurney there, lifted the gurney up, and now you're just going to push it to the ambulance. So your initial velocity here is 0. How much work is done by us? You want to put friction or no friction? Still no friction here? So no friction. Make life easy on you. Are you going to move at constant speed? Can't be constant speed, we give you acceleration, right? So it can't be constant speed. Can we find what that force is? What's the work done? So the question, find the work done by the EMT. Well, I know work equals what? Isn't that force times the distance times cosine theta? Let's see what we know. Do we know what the distance is? Distance is what? 1.9. Do we know what the angle between the direction you're pushing and which way you're moving? 0, cosine of 0. Do we know what the force is? No. If I know what that force, I'm done. But wait a minute, we just finished Newton's law. If there's no friction, what's the net force? Equals mass times acceleration. If there is no friction, your net force is the pushing force, whatever force you're pushing with. And that should equal to what? The mass. What's the mass of that child there?
27.
27. I'm neglecting the mass of the gurney here. Or 27 is the combined mass. What's the acceleration? 0.55. So now we know what that force is. So the force is actually a pushing force. That's what the force is. 27 times 0.55.
14.85.
That's 14.85. Once you get that force there, now you come back with it and plug it in here. You go, the work done by us or by me pushing that child or by you is going to be 14.85 times 1.9 times cosine of 0. .2 joules. Now, let's add more to that story. Let's say you realize the child is really okay there, but you're going, you know what? I need to lose some weight. I need to exercise. How far I got to push the baby to burn 140 joules? So now you're zigzagging, running around the corner because you said, I made it all the way. I want to lose some weight. I need to burn 140 joules. I need to waste some energy. So let's reverse that. Here's part 2. How far? Must you push the patient run with the patient, whatever you want to call it, to do 140 joules of work. Now we can work the problem backward. We know the work equals what? F times x times cosine theta. I'm assuming the same pushing force, the same acceleration. I'm not changing that. Otherwise, I'll give you numbers for it. The acceleration of this number, that number. So I know this is 140 equals the force. What was the force from part 1? 14.85 times x times 0 cosine of 0. I'm sorry, times cosine of 0, not 0, which is 1. That's a 1. So 140 equals 14.85x. X will have to be what? About 9 something, 9 meters. 140 divided by 14.85, 9.4 meters. About 30 feet. Push them 30 feet at that acceleration, and you can burn about 140 joules of energy. Now remember, if the object does not move, if you're pushing a weight and you can't lift that weight, or you're pushing on the wall and the wall is not moving, the work done by you is 0. So if there is no movement, the answer is 0. So 0 distance, just put that in writing. 0 distance implies what? 0 joules of energy. 0 work. So if you push on your car that's stuck in the mud, you push, the car is not moving, you did no work. You say, I'm tired, I'm sweaty, I'm exhausted. No work done by you. Let's try another example. You watch that Deadliest Catch. It is Deadliest Catch, that show on TV. Anyone ever seen it? Mm-hmm. And before, they throw that cage in the water, they put it on this lift, and once they lift the lift up, the cage really slides down into the water. So basically the component of the weight drags it into the water. We use that logic for a lot of places, like these boats, lifeboats on cruise ship. Some of them actually you can just bring them down by a winch, but there's little incline, small boats that have these inclines, just pull them in and the boat will slide down using gravity. You don't have to push that hard. If you tug the boat behind you, you'll notice that once you go in the water, the back wheel goes in the water, sinks in. You take that, loosen that rope, because the angle becomes like this and the boat will slide off that ramp that you carry the boat on it, the trailer. So that logic is used all over. So that's called a gravity escape problem there. So let's try an example here. We have a container, could be lobster, could be ship, could be anything. But we have a box here that weighs 4,970 kilograms. 4,970 kilogram. Heavy box. And this one slides down 5 meters. So the box was somewhere up here and slides down. Let's say it was at 2.5 meters height initially. We'll see if we need that. And slides down 5 meters. Gets to the bottom. How much work was done by gravity? Oh, gravity now. How much work was done by gravity? Now when you look at the box, you go, well, the box was moving this way. That's the direction the box was moving. But which way is gravity on the box? Gravity's down. Straight like this. That's the force, which is the weight, which is mass times gravity. You get an angle theta here between them. Now I can do a couple of things here. Since I'm looking for gravity, I can find what component of that weight in that direction. Right? So how do we figure out to find that component? That means I need to know what this angle is, or this angle. Can we figure out what that angle there? Well, that's not this theta, so let me call them different names. Let's call this angle beta. B, beta. I don't want to use theta because that's a different angle. This is theta. According to my picture, I labeled this theta, so this is really theta. That's beta. Can we find what beta is and what theta is if we need them? Beta is what? We know sine beta is the opposite, which is what? 2.5 over the hypotenuse, which is what? 5. Sine beta is equal to a half. Beta will be the inverse sine of 1/2. Should be 30 degrees, right? So I know that's 30, this is 60 degrees, because they have to add up to 180. So now you look at your picture, you go, this is what I have. I got this angle, which is what? 30 degrees. I got the box down. I get the weight down, mg. If you want to find that component, remember, there's the normal force going that direction. I can take this vector, the weight, I'm going to erase it here, and replace it with these two values. mg what? Sine theta. And this one is what? mg cosine theta. I didn't mention anything about friction here, so there's no friction. So how much work was done by gravity to move the box from here to there? What's the work to move it from here to there? So the work done by gravity, because gravity was the only reason why the box slid down, is equal to the force, and the force is what? It's this value times that distance, which is what? Times 5. Work is force times distance. Let's plug in the numbers and see what we have. 4970 times 9.8 times sine of 30 degrees times the 5 meters. And I got 121,765 joules. 121,765 joules.
So are we using beta or alpha?
Well, if you're going to use the sine, you got to use that angle. If you try and find that component. Yep. If you decide to use this angle, the 60 degrees, notice this side is what? Adjacent. You use the cosine. So if I use this one, the 60 degrees, I'll use cosine because I want to find the portion of that in that direction. Now I could have done the problem much easier than doing all this work. And that is, here's my story again. This is the ramp, the box here. This is 5 meters. I get the weight down, which is mass times gravity. And I got this distance to be what? 2.5 meters. For the box to go from here to here, it really doesn't matter which way it is. We don't care how long that ramp is. You can make it much longer, and that answer will be the same. Or you can make it straight down. If I make it straight down, what's the work done by gravity? Let's look at gravity. Gravity is pointing down. That's mg. That's the weight. And what's the distance from here to here? 2.5, right? I bet you if we do the math here, we'll end up with a 121,765. So let's see, the mass, what was the mass for that one? 4970. Gravity is what? 9.8. And what was the height? 2.5. Let's multiply these numbers. I'm confident the answer is going to be 121,765. I won't even push the button. I'll let you push the button to prove it. Yep. Because we're looking for the work done by gravity. Gravity traveled this far. So when you're moving people to an apartment and you got these trucks that have the ramp in them, it doesn't matter if the ramp is very steep. Like if this is the truck here, and this is the road here. It doesn't matter if the ramp is like this. Doesn't matter if the ramp is like that. Doesn't matter if the ramp is like this, like this. The work done is going to be the same. The difference between them, the longer the ramp is, the less I have to apply the force. Because basically, if the answer to be the same, if x increases, if that distance increases, that means what? The force has to decrease. So it makes it easy on me. I don't have to push that hard to get that box from here to the truck. I could just pick it up from here, directly below the truck, and move it up. And that's the same work if I pushed it on this ramp, or that ramp, or this ramp, or that ramp. The work will be exactly the same. The difference between them, that requires less force than this one, this is less force than this one, this is less force than that one. And that takes us to handicap. Handicap railing. You'll see these long railing. The bylaws state, I think 13 foot should have 1 foot rise in Massachusetts. I'm sure it's the same all over. For every 13 feet in this direction, I think 13 or 12, I'm not 100% sure, 13 or 12, you rise 1 foot. You can Google that. So the ramp has to look like this. Well, 13 feet is a long ramp there. So people said, well, I don't want to put 13 feet in front of my house, especially if you have 2 feet high or 3 feet high to the door. 13 times 3, that's 39 feet long. So they go around like a zigzag. They start to go like this. Each time you raise it just half a foot, half a foot. So this way you're not taking the whole yard. Otherwise, that ramp will cover the entire yard there. It might be in the middle of the road just to reach that one. And the reason for that, we want to make sure that people in the wheelchair, they don't have to use, like, you don't need massive muscles to push that wheelchair up that ramp. Because if you make it steep like this, that'll get them there, but boy, they have to work really hard. And if you're an older person, senior citizen, 80 years old, 85, 90 years old, you don't have the muscle to push up the ramp there. But the work done on this ramp or that ramp will be the same. This will require, like, because the distance is small, notice that distance is much smaller than that distance. This one requires a force probably 5 times larger than this to get that chair to go to the ramp. So let's see if that's really the case. We'll do some math problem with that truck there, loading a truck. So you want to load a truck. There we go. Here's your truck. There's the box. One option, it has a big tires, huge tires. So you get to see the truck. So one option is you pick the box and you move it straight up there and you put it in the truck. That's one option. The other option, again, here we go, the truck. Oh, I gotta make the wheels big. Massive truck, massive wheels on it. The other option to use a ramp there. Push it on the ramp. So one option, we're going to move it straight up, constant speed. This option, pick it up, move it at constant speed, and put it in the truck there. We'll call this height H there. The other option, this same box, same height, but I'm going to push it on a ramp there. So we're going to take the box here, and we're going to push that box on the ramp. I'm going to be pushing on it in that direction. Let's say the distance L here. I'll give you numbers, or maybe without numbers. We'll say no friction again.
Just the left, very left side of the page, we can't see.
Oh, I can't zoom in actually, no. Yep, no problem. So the other part, I'm going to push the box up the ramp there. No friction. You want to move at constant speed here too? Let's find how much work done. Again, I'm pulling let's start with this one. I'm grabbing the box, pulling on it upward. So I'm doing the work. I'm pulling up and the box is moving upward. So the work done by me is equal to the mass of the box. It's force times, I'll just put this, force times distance. Let's start with that. What's the force by me if I'm moving at constant speed?
0.
Try again. Constant speed. If you're looking at the box, what are the forces on the box? There's me pushing up, that's me, and there's gravity pushing down, mg. If you move at a constant speed, that means your acceleration what? Not 9, that's when you drop at 9.8. Your acceleration is 0. Constant speed. Acceleration, change in speed, change in velocity. So if you move at the same speed, there is no acceleration. That means these forces have to equal to each other. The net force equals mass times acceleration. So if your acceleration is 0, the net force has to be 0. That means the force by me should equal mass times gravity. And the distance is h. And that's the work done by me. Okay. I need to know what this angle theta is. I decided not to give you numbers to just challenge you. What is sine theta equal to? Isn't that the opposite over what? The hypotenuse? Opposite is h, the hypotenuse is L, the length of the ramp. I don't want to give you numbers. So what's theta? The inverse sine of h over L. So if I gave you some numbers, you can just take the numbers, put them in your calculator, hit the inverse sign, you can find what theta is. Now again, let's look at that box. We got that force this way. I'm pushing up. I already drew it wrong. I'm pushing up with the value of what? F going up there. The normal force this way. And the weight down. We can take this force, break it down to x and y value. mg sine theta and mg cosine theta. Again, if you move in a constant speed, that means your acceleration is 0. Definition of acceleration, change in velocity over change in time. If your velocity is not changing, your acceleration is 0. That means these two forces must equal to each other. So the work done by me, again, what's the work done by me on this truck here? It's the force times the distance. What's my force? My force is what? mg sine theta times the distance, which is what? Isn't that L, the distance? We moved it all the way the whole length of that ramp from here to there. So that's equal to what? mg sine, wait a minute, what's theta equal to? From this one. Now the inverse sine? Theta is the inverse sine of h over L. If you remember from trig, if you took the trig, these guys, when you see sine, inverse sine, they cancel each other out. So I end up with mg h over L times L, and what happened to the L's? Cancel each other out, and you end up with what? mg times h. Is this the same answer we found here? So regardless if you pull it up or push it on a ramp, The work done by you is the same thing. I just want to prove the math behind it. I could have used some numbers and made the problem more fun, but I figured, why change today? Let's keep it ugly. Maybe a couple more examples on work, then we'll say we're done with it. We'll go to the next one, next topic. So let's try another one. Here's your car parked here. You stopped on a hill. This is theta. Has a mass m. Now when you look at the car there, and the car is moving down the road here, there are three forces acting on the car. You get the normal force. Again, the engine is not running. I get to the top of the hill, I forgot the emergency brake, I never even parked the car. I saw somebody, I got excited to see him, I opened the door and ran to them. You start looking, you see your car rolling down the hill, like, uh-oh. So maybe you're in the service. You know, you've been serving our country for the past 3-4 months. You're in Iraq or in Afghanistan. You come home, you're excited to see your wife, your husband. You see them there, you open the door, you run to them to give them a hug there. Oops, there goes the car. So the forces acting on that is the weight here down. The normal, you forgot to put the brakes. There's a friction force pointing. Where is the friction force? If the car is moving down, the friction force is going to be going that direction. That's the wind resistance, the wind pushing on the car backward, the tires rubbing on the road, there's a friction force. And now the car starts to roll down a distance d. So what is the work done by, let's begin with gravity. How much work done by gravity? Anyone? So here's the picture again. The distance is d. There's your car. There's the friction force. Yes. Yep. Yep. So this is going to have a component in this direction, mg sine theta, right? It's going to have a component in this direction of what? mg cosine theta. So the weight is gone, being replaced with these two. So the work done by gravity, this is gravity, mass times gravity here. The work done by that is equal to this component times that distance. That's a positive. mg sine theta times the distance traveled, which is d. That's the length of the ramp, or when the car rolled from here to here. What's the work done by the friction force? By a friction force, how much work is done? Is that a positive or a negative? Negative. Why? The friction force pointing in that direction, you're moving in this direction. That's cosine 180 degrees. What's cosine 180? Minus 1. So it's Fk, whatever the friction force, times the distance d. In case you're wondering what is Fk, Fk equals what? Mu k times n. So you can find what Fk. And we know what n is. Mg cosine theta. So what is the work done by the friction force? Minus mu k times mg cosine theta times d. But it's a minus. That's the key I'm trying to make here. Work done by friction, it's a negative value. What is the work done by the normal force? That's 0. Why? Work is what? Force times distance times cosine theta. When I say cosine theta, that's the angle between the force and the direction you're moving. The force is the normal force. The distance traveled is d. But what's the angle between this and the direction you're moving? That's 90 degrees. What's cosine of 90? 0. So the work done by the normal force is 0 joules. Okay, I think we got the idea of what work is.
Can you leave that for 1 second?
I'm going to leave it. I'm just going to shut the video.